Hey guys, so we're doing now episode 8, Algos in 10, basically a very interesting version of Monopoly with Dijkstra. So we go from basically the Mediterranean Avenue all the way up to the amazing boardwalk. We also deal with this type of money as well with Monopoly. So let's just hope people remember what Dijkstra's algorithm is in terms of like the shortest paths. And make sure you subscribe to the channel, as I'll show you very quickly in a very cool way how we actually modify Dijkstra's algorithm and apply it multiple times up to like, I don't know, boardwalk times for this to work. Of course, also subscribe to the channel because you also want to be able to collect $200 if you sub. So for this problem set, we're going to use a very interesting application of Dijkstra's shortest path algorithm regards to residual graphs to determine what is the best way to win the game of Monopoly, aka get boardwalk and don't lose your money, without going to jail 4 times, which is terrible because every time you go to jail, you lose 1/4 of your money. If you go and lose all your money, you get bankrupt. And that is not something you want to have in a Monopoly game. So let's try to avoid bankruptcy when we try to solve this Algos in 10 problem applying Monopoly. So before we actually try to solve a Monopoly problem, I'm going to know what the type of shortest path algorithms there are. So what does it mean to have a shortest path in a graph? Well, you have any general graph G equals VE, and you basically have the nodes from the starting node S to the node T. And anything that shows that the weight of S is less than weight of T, and that is the min of all the shortest paths from 1 to n shortest paths, is considered the most optimal shortest path. And if all that sounds like math gibberish, let me show you an example very quickly. We also have 3 main types of shortest path algorithms that a lot of people in computer science use, such as our one we're about to use today, Dijkstra. Then we have Prim's shortest path, or actually it's for min-span tree, but also could be applied to shortest path. And finally, Kruskal's shortest path min-span tree algorithm. We're going to use only Dijkstra because Dijkstra is the most popular and the one that people actually get wrong a lot easily because of not being able to understand the priority queue. So let me show a very short example with a very simple word, champs, to explain how Dijkstra's algorithm. So now we have an example of applying Dijkstra's algorithm. So from the beginning, we have the node CHAMPS, or champs, and we want to find basically the shortest path. So from the beginning, we have 0 and then infinity for the rest of them. Infinity means you don't know what the distance is, so distance is unknown. If you want a more concrete example of using Dijkstra's algorithm, I would suggest using a CLRS chapter for it, or any other leak code or general like computer science reference to understand Dijkstra's algorithm. So we obviously start from the node C and we determine which is shortest path. Obviously 1 is, so we say C is visited, and then we also update the distance from C to A to be 1. Next, from A, we can't go back to C because it's a cycle, and you can't have a cycle in a min-span tree or shortest path. So what you can do instead is go to the 2 neighbors of A, which is P and M. Obviously P is the shortest path here. So you change P to be 4. Finally, you basically choose only P to have one neighbor S, and therefore S is going to be 10 total. And there is your shortest path, which is the path of P of C, A, P, S. A, capitals, the caps. Of course, not much of a Washington Capitals fan, but they are doing pretty good for the playoffs, hopefully. And then, of course, you'll see that all of the nodes are visited once you finish the Dijkstra's algorithm. So you update H to be 2 here, and then M to be updated to 6. And that's all the distance you'll need for this algorithm. Now I'm going to show you how to apply Dijkstra's repeatedly to solve our Monopoly problem. Of course, Dijkstra is tough to understand, so make sure you go over this example yourself to understand how Dijkstra works. So the problem setup is like this. You're playing a game of Monopoly, right? So you have 40 total squares you can go to a Monopoly. And you can go at most to jail 4 times. which means every time you go to jail, you lose 1/4 of your money. So you can imagine if you go to jail after the 4th time, you get bankrupt and you lose the game and you don't get happy of your total M money. In addition, you also, every time you buy property, you do M total monopoly money minus the G of I, where G of I is the cost of property I in graph G. And of course, you know, if you played Monopoly before, the most cheapest one, shall we say, is going to be the graph G of Mediterranean Avenue. While the most expensive, of course, as I just shown you earlier in this video, is Boardwalk, or in this case, G of BW. Correspondingly, we choose the G Mediterranean to be basically the first initial graph, G1, and then GBW to be the final initial graph, G of 40. Now, why do I do this in type of notation? We want to show there's a cyclical usage of Dijkstra in this application. So let me quickly show you now how we draw this in a cyclical fashion. So to draw this application cyclically, we gotta first have a G0, which is of course your starting point, appropriately named Go. Then you go to basically the first square, where you have the Mediterranean, Gmed. And you gotta see these are like mini Dijkstra graphs here. They're acyclical. They're actually not in a cycle themselves, but the entire graph algorithm is cyclical. So here we have G of Mediterranean. And we do it all the way up to the G of Boardwalk, which is the last official graph, residual graph in this algorithm. So this is G of Boardwalk. However, there's a catch to the algorithm. Each time you traverse an edge, there may be a jail edge, and you want to avoid the jail edge here. So avoid a jail edge, because every time you go to jail edge, you lose 1/4 of money. Avoid the jail edge, just like the real game of Monopoly. Avoid rolling whatever number from 1 to 12 to get to jail. Because every time you go to jail, you lose automatically 1/4 of your money. So appropriately, there are 4 total jail edges in this Monopoly game that we're trying to avoid with using Dijkstra's algorithm. We could generalize this to n, but that becomes a bit of an NP hard problem. So we're gonna keep it to 4 for now. So let me show you how we do this in terms of removing and adding the edges. It's a bit weird, right? You don't know what the jail edges are, but you at least know where they're located. So if you remove them, you can make a big brain move and I already could tell you where edges you're supposed to go in general. That's the beauty of this algorithms. You don't have to do anything fancy damn programming. All you have to do is just remove and add edges carefully, and of course include backtracking if you're gonna go back to Go to get this algorithm started. So let me show you how the algorithm works. So the algorithm works like this. We have our original graph, basically of all these residual Dijkstra graphs from G of Boardwalk, no, G of Mediterranean, sorry, all the way to G of Boardwalk. With G of 0 being Go, basically. So the first thing we notice is that there is a subset J of E total edges that lead you to jail. So you want to avoid that, obviously. In addition, you also have 40 copies because there's 40 total squares Monopoly. We're also including the railroads, community chest, and chance cards. But we're not going to really include them in terms of money because it could really go either way. You could either lose money or gain money based on community chest or chance cards. For example, if you say like the bank error got into favor, you would have M dollars plus G of I for your total money in Monopoly. Otherwise, if you actually owe the bank some money or you have like a mortgage debt, it'll be minus of I. That's like the total money we have for this entire Monopoly game. ensure this thing is greater than or equal to 0, because otherwise that is bankruptcy and you lose the game and this thing does not work anymore. So avoid bankruptcy by avoid going to jail too many times or using up all your money to buy all the properties. So let me show you now how we actually optimize this with the removing and adding. So to continue the algorithm, we first basically determine J1, J2, J3, and J4 as the jail edges. So let's take a very simple example. Let's just say, for example, there's only three squares in this really easy Monopoly game. You have just go, G of Mediterranean, which is like this. And let's just say, for example, it just costs $60 for rent. So you have total of M dollars minus 60 if you want to buy Mediterranean Avenue. If you want to be a bit too haul and a bit show-offy and want to, be greedy, you can apply to Boardwalk already, which is G of Boardwalk, G of BW, which each time you take the rent is minus $400. So obviously you want to be more optimal and choose G of Med first. First, we have to remove the jail edges. So remove for all I less than equal to 4. Sorry, from all I, math, from all I 1 to less than equal to 4, all the jail edges in Monopoly. Because otherwise that would be a bit of a problem, solving the problem. Next, we have a residual copy of a graph for G of I that's from the node U. The node U would be a residual copy, so basically add an edge. Add an edge from copy of U, part of G of I, to a particular copy of node V, G of I. And this basically means when you have a node U, let's say for node U here, you remove a jail edge here, you basically copy over a portion of it to V and remove the identical jail edge. This should remind you vaguely of how we actually use bit of pruning trees or min-span tree to build and remove tree edges. Of course, you have to be very careful backtracking as well, which means this should go the other way around. If you remove an edge here, you should also remove an edge here. Ensure that this algorithm works for both ways, both from Go to Boardwalk and then from Boardwalk back to Go. Ordinarily, Monopoly is not played that way, but this algorithm is cyclic, so it goes in both directions. So let me then wrap up the algorithm with regards to basically the feasible paths and the runtime. So to wrap up the algorithm, we basically say for the following. For each feasible, which means path that you can actually walk to in Monopoly, each feasible paths, S, which means basically the go or the starting point, to T, which is the graph for Boardwalk, we call essentially Dijkstra's algorithm, Dijkstra, on each residual graph. We continue this until we have either the maximum amount of money we can spend that's not 0, or we go bankrupt and we fail the game and that our money is 0. Sorry, our money is 0. So as long as you even have just $1 left, you win the game. This is like how Monopoly works. As long as you have the most money left without being bankrupt, you win the game. So let's go over runtime really quickly and tell you what's going on next. Yeah, this is a really short Algos in 10, but Monopoly is important in terms of understanding chance and probability and how residual graphs actually work in a real application problem. So runtime is very simple. We have a graph, G equals VE, right? In addition, we also have the following. We have 40 times V. Now this is called the magnitude of V, or how many, which is the total number of vertices we have for each residual graph. We also have 40 times E, the number of residual edges for each graph. Now, the reason why we use residual graphs is because later on, when we get to really advanced algos in 10, we learn about Ford-Fulkerson. It'll help you understand why we use residual graphs to basically find max flow, min cut. This is like a precursor to that type of algorithm. And of course, the vanilla Dijkstra would just be the following. It would be O of V plus E log of V. And that is your algorithm runtime. Like pedantically, we could make it like this, O of 40 times V and then plus 40 times E, but you know how weird that would be, right? Because in any algorithm runtime, you get rid of a constant. So it doesn't matter how much there are, even 1 million or 2 billion constants are gone, gone, and gone. So that is the official runtime for using Dijkstra's algorithm. A minor improvement we could do to make this a little bit better is use something called an adjacency list, in that we actually basically store the neighbors of each visited node. If you guys can also find a solution to using the adjacency list, that would be pretty awesome. That might be like a bonus Algos in 10 problem or like a revision. But for leak code and general solution with regards to applying Dijkstra's algorithm with residual graphs, this is good to go. So yeah, that's it for the Monopoly application with Dijkstra's algorithm graph. So next time we'll go over some canny edge detection with AI. You know how like in canny they have pin fills and stuff. Canny edge detection AI, and then finally we have AHT, the abstract hashing type. So hold on tight, because then we'll really get into some really good stuff for dynamic programming and more advanced graphs with Algos in 10. So thank you. This is episode 8, Algos in 10 with Jason Liu. Make sure you don't lose your money when we play Monopoly next time.